name is Subodh, and today I am going to present our work titled Localization of Smart Infrastructure Fisheye Camera in a Prior Map for Autonomous Vehicles. The objective of this project is to estimate the pose of an elevated, static, downward-looking fisheye camera in a given map built by a combination of satellite images and LiDAR mapping data. In this slide, one can see four different images. The leftmost shows a fisheye image we have obtained from our simulator. The second is a satellite image whose scale is known in metric units, and the next two correspond to ground intensity and height data obtained from the known LiDAR map. The motivation behind this work stems from improving the safety and situational awareness of autonomous vehicles in an environment with occlusions. A solution to this problem is to augment the infrastructure around the autonomous vehicle with static fisheye cameras, which can sense a very wide area and relay this information to the autonomous vehicle for its perception and planning algorithms. However, this solution is possible only after we localize or register the static fisheye camera in the map on which the AV operates. The fisheye camera localization problem forms the topic of our presentation. We follow a two-step process to solve this problem. In step one, we match features between a rectified fisheye image and a satellite map using a deep learning-based feature matching algorithm called SuperView. Once the matches are established, we solve a PNP problem to determine the initial camera pose. As the metric scale of the satellite image is known to us, the initial camera pose we obtain here is in metric units. In step two, we refine the initial camera pose obtained in the previous step by maximizing the mutual information between the fisheye image and the LiDAR map. The process involves calculation of individual and joint probability density functions and entropies for both LiDAR intensity and fisheye grayscale values for a given fisheye camera pose. The goal of this step is to search for the camera pose which maximizes the mutual information between the fisheye image and the given LiDAR map. In our project, we use a grid search-based method to solve the optimization problem. Having localized the fisheye camera, we proceed to verify the quality of sensor registration. In this slide, we project the LiDAR map onto the fisheye image using camera pose estimates obtained from step 1 and 2, shown in left and right respectively for two different locations in real-world settings. On the left, one can see that the LiDAR points, which are colored in cyan, are not well aligned with the fisheye image, as evident from the misaligned road markings. But after refinement, as shown in the image on the right, the misalignments are substantially minimized. This is observed at both the locations we present here. In the previous slide, we presented qualitative verification of camera registration. In this slide, we present quantitative results. We measure the GPS coordinate of certain points which are shown in green on the images here. This serves as our ground truth. Next, we project these GPS coordinates onto the fisheye image using the results obtained from step 1 and step 2, shown in red and blue respectively. As shown in both the images, the results from step 2 have lower reprojection error when compared with results from step 1. This shows that the MI-based refinement of camera pose improves camera registration results. Summarizing our contribution, we proposed a two-step approach to register a fisheye camera in a prior map. We present results from both simulated and real-world settings. We performed both qualitative and quantitative validation of our approach. This brings me to the end of my presentation. Thank you for your time, and we are ready to field your questions.